This is the third video supplement for CIS 251, Grand Valley State University's course on computer organization and assembly language. In this video, I'll discuss how many bits of input a combinatorial circuit needs. The first video provided an overview of the course and showed how to build a combinatorial circuit, which I presented as a blue box that can answer yes/no questions about integers. This box uses a light as output, on for yes and off for no, and a series of switches to specify the integer we're asking the box about. This video will discuss how many switches the box needs. In the fourth video, I'll talk more about the meaning of the switches. In particular, I'll discuss encoding integers in binary. The fifth video will discuss hexadecimal and other number bases. Imagine our prime number box with just one switch on it. How many different integers can we ask this box about? We may want to ask about any integer at all, and there are of course infinitely many of them. But since this box has only one switch, it can distinguish between only two requests. Whatever integer we mean by turning the switch off, or whatever integer we mean by turning the switch on. If we want the single piece of hardware to distinguish among more than two integers, we need to put more switches on it. So how many integers could we ask this box about if it had two switches on it? Well, 4. With two switches, there are 4 combinations of switch positions: off-off, off-on, on-off, and on-on. And we can assign a different integer to each combination. This means that a box with 2 switches can answer a question about any of 4 different integers. How many different integers could we ask about if we put a third switch on the box? Let me show you how to figure that out. Let's begin with the 4 combinations of 2 switches. Then add a third switch to each of those 4 combinations. For each combination, we now have 2 choices: turn the new switch off or turn the new switch on. Thus, as you can see, given 3 switches, there are 8 distinct combinations of switch positions, which means that a box with 3 switches can answer a question about any of 8 different integers. Just to be clear, let me show you a different view of how each of the 4 combinations of 2 switches defines 2 distinct combinations of 3 switches, thereby doubling the number of combinations. This doubling pattern continues indefinitely. Let's begin with one switch, which has 2 possibilities, off and on. Adding a second switch doubles the number of combinations to 4. Adding a third switch doubles the number again to 8. 4 switches give us 16 combinations, 5 switches give us 32, and so on. How does this generalize? If I give you a box with n switches on it, how many different integers can you ask that box about? The answer, of course, is 2 to the n. So now that we know that n switches allow us to encode 2 to the n different integers, the next question is, which 2 to the n integers? That will be the subject of the next video. Thanks for watching.